Welcome guys. In this video, I'll be talking about resting membrane potential. But before we actually start to study the resting membrane potential, it'll be very good if we understand first the electrostatic physics behind it. Then it is very easy to understand resting membrane potential, right? So to start with, that's why the flow of our lecture is gonna be first, we're gonna learn about charge, then electric field, then potential energy and potential, which are two different terms, they are not same, and then we'll study the main concept of membrane potential, right? So what is charge? So basically in this universe we have four different kind of forces. We have electric force, magnetic force, gravitational force, and weak nuclear force, and each of these forces have their corresponding particles. For example, for electric force we have what? Charge. For magnetic force, we have magnetic poles. For gravitation force, we have mass. So anything that is having mass can exert a gravitation force. And then last, weak nuclear force, we have nucleons, right? Now, the important thing to know is that each of these fundamental particles corresponding to each field, each force actually produces the distortion in space-time around them to produce their corresponding field. For example, a charge will produce electric field, a magnetic pole will produce a magnetic field, a mass will produce gravitation field, like that. They cannot produce each other's force, right? So for example, we have a charge here, Q, and it will distort the space-time curve around it like that. So this is a charge and producing electric field. Now how do we decide the direction of this electric field? So for this, what we do is we assume that we are bringing a positive charge, and then we measure the effect of this charge on that. So for example, we bring a small charge Q, right? Now it's also very important to notice, although it is very common sense, that these things we can't actually see. If two charges are together nearby, we can't actually see these lines being produced, but we can measure the effect. So if you bring a small charge in its vicinity, what will happen? We'll experience, if this is positive, that this positive charge will move away. Therefore, we'll give the direction of this electric field like that. On the other hand, suppose if we have a negative charge, it will also produce electric field. But since in this case, what will happen is, if we bring a positive charge, this positive charge will be pulled towards it. That's why in this case, the directionality will give like that. So both are producing electric field, the difference is in the direction. So with this, I have told you what is charge, I have told you what is electric field. Okay, now we have to understand what is potential energy and potential. Now these two things also apply to every other forces. They also apply for magnetic force, they also apply for gravitation force, they also apply for weak nuclear force, but we are studying these two with reference to electric forces, right? So what is potential energy? So suppose this small charge which we are having, if we try to move it in electric field of this charge, there will be changes in the energy of this small particle. Either it will lose energy or it will gain energy. For example, if we have to move this particle from point A to point B, in this case, what will happen if we move it from point A to B? We have to give it energy, right? Because this electric field is trying to push it away, but we are moving it against it. So we have to give energy to this particle. So when these particles move from A to B, it will gain energy, right? So in this case, we'll give the value of energy change as positive. On the other hand, if the particle is at B and we have to move it from B to A, in this case, we don't have to push it. Rather, it will automatically go from B to A because of the electric field. So in this case, we don't have to give energy to the charge. Rather, it will be giving energy automatically outside to the rest of the universe. So in this case, the energy change will be negative, right? So this energy change is what we refer to as potential energy, right? And then what is potential? Potential is nothing but potential energy divided by the amount of charge which we were moving. So this, to give you an example, suppose this was 10 coulomb charge, this was suppose plus 2 coulomb charge, and from moving it from point A to B, suppose there was energy change of 4 joules, right? So 4 joules will be our potential energy of moving this 2 coulomb charge from point A to B. And what will be the potential? We just divide it by the charge, so it will be 2 volts. Okay, one thing more, the unit of charge is coulomb, the unit of energy is joules, and the unit of potential is volts, right? So here we got a potential energy value of 2 volts. What does it mean? It means that if we try to move 1 coulomb charge from point A to B, in the electric field of this charge, we have to give 2 joules of energy. Conversely, if we have to move 1 coulomb charge from point B to A, again it will be 2, but it will be minus, because in this case energy will be released. So this was the concept of charge, electric field, and potential energy. I hope you guys could understand all this. If not, please go and rewatch it, because for rest of the concept it is very, very important. Okay, now we come to our main concept of resting membrane potential. Let's start as if you know nothing about this topic. So basically what happened was, when scientists took a cell, what they found out was the cell membrane is not neutral. It is having some electric field, and in this direction all around the cell surface, right? And the other way to write it is in potential, and the value they found out was minus 70 millivolts. Actually this thing differs. For example, if we measure it for a typical neuron, it will be minus 70. If we measure it for skeletal muscle, it will be around minus 90 millivolts, and for epithelial cell it will be minus 50 millivolts, but it differs. So this value of potential is what we are referring actually to as resting membrane potential, right? Which is the potential across cell membrane when the cell is not stimulated and is in resting condition. Resting condition means it is not stimulated either by surrounding cells or mechanically, right? But if it is stimulated, then this potential changes. It becomes positive 20 millivolts. So this change in potential when it is stimulated, that we refer to as action potential, which you're going to learn about in our next video. So this is the definition of resting membrane potential. And here, since we have studied all those concepts, so we can convert it and see its meaning actually. So for example, here we got a potential of minus 70 millivolts, right? That means that, and it is given for point B to A actually, point B to A. This resting membrane potential is given of any point which is just inside the membrane with respect to any point which is just outside the membrane, whose value is minus 70 millivolts, right? That means if we take 1 coulomb of charge and move it from point A to B, the particle will be releasing energy, and how much? 70 into 10 to the power minus 3, because it is milli. So 70 to 10 to the power minus 3 joules. So 1 coulomb charge, if we move 1 coulomb charge from point A to B, this much energy is released, right? So this was the concept of potential. And you can also equate this sign with the direction of electric field. See, because suppose this is suppose this is a cell membrane, and you're moving 1 coulomb charge from point A to B, right? and it is releasing energy. This much energy it is releasing. That means that there must be electric field in this direction, right? That's why it is releasing. No, if we move 1 coulomb charge, if I'm moving 1 coulomb charge from point A to B and it is releasing energy, that means the electric field must be in this direction. That is, it should be pulling it. That's why it is releasing energy. So now you can equate it all you can actually see the actual meaning of potential and electric field, right? Okay, so now once you have understood that the cell membrane is having electric field in this direction all across its cell membrane, and the potential corresponding to it is called as resting membrane potential. So now we have to understand. So we have answered this question: what is RMP and action potential? Now we have to answer how resting membrane potential is developed. So we know that the electric field is in this direction. Suppose this is inside intracellular fluid or space, and this is outside. And we know that the electric field is in this direction. Now, electric field in this direction can be developed in one of the three ways. One is that the cell accumulates positive charge outside and zero charge inside, or it accumulates negative charge inside and zero charge outside, or it can accumulate positive charge outside and negative charge inside. So in all these conditions, electric field will be in this direction, which is observed by the scientist. So the question is, out of these three ways, which method does cell use? So the answer is, cell uses this method by accumulating more positive charge or ions outside and more negative ions inside, right? Now the question is, how does it do so, and what does it mean when we say that more positive charge outside and negative charge inside? Now that we have this, now we have to answer. Okay. So again, this is our outside space, extracellular fluid, and this is intracellular fluid inside of the cell. Okay, now initially what happens is, on both sides charges are present and they are equal. So for example, positive negative, positive negative, positive negative, like that. So as you can see, initially on both sides charges are present. It's not that there is no charge. Charges are present, but the net charge on either side is zero, right? Okay, one more thing. Here the ions which are most common are sodium for positive and potassium. So we are gonna assign those ions to these. So suppose we have potassium, 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 Na, 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 same here. K, K, and K. Right? We are not assigning any molecule or element to the negative charge, because that's not important to understand the concept right now. Right? So initially, this is the condition. On both sides, charges are present and they are equal, so cancel out each other. So the first thing that happens is, to develop electric field in this direction, a cell starts to make negative protein and put it into the cytoplasm. So it will start to make negative proteins, negatively charged protein, and put it into the cytoplasm. So what will be the condition now? This zero will become negative. So there will be a development of electric field in this direction, right? Now let's see how cell further strengthens electric field in the same direction. Okay, the next thing that happens is, cell has a pump which we call as sodium potassium pump. It uses ATP and pushes 3 Na ions outside and 2 Na ions inside. So suppose these Na ions it will push outside and these 2 K ions inside. So now what will be the condition? Watch here. we have K positive, negative. This was not disturbed. We have negative, 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 negative. This was not disturbed. Okay, so this pump, sodium potassium pump, pushed 3 sodium ions from inside of the cell to outside, right? So it will go from here to there. So it will occupy this, and then we have one Na ion extra, which is not bound to any negative ions. Similarly, these 2K will come inside and they'll occupy this, and here one negative charge will be left extra. So now here you can see on the inside there is more accumulation of negative charge, and outside now there is net positive charge. So this negative will become more negative and this zero will now convert into positive. So this electric field will further strengthen in this direction. But still, it's not finished. There is one last step to further strengthen electric field in this direction and develop electric field, which is now now here, as you can see, since the pump, this pump, NaK pump, is pushing a lot of sodium ions outside and a lot of potassium ions inside, therefore on outside there will be more concentration of sodium ions, and on the inside there will be more concentration of potassium ions. And according to the simple law of diffusion, the sodiums will try to move in and potassiums will try to move out. But sodium will not be able to move in because there is no such channel for sodium to move in. But when it comes to potassium, cell has another channel which we call as potassium leaky channels. So since the concentration of potassium has increased on the inside and we have potassium leaky channels, therefore the potassium ions will start to move outside, right? So now what will happen? These were our negative proteins. Suppose these will move out. So we have more extra negative ions. Now here, as you can see, because some of the potassium ions under the influence of concentration gradient cross to that side, therefore they leave these negative ions as it is. So we have more accumulation of negative charge on the inside. So negative charge will increase on the outside, whereas the potassium ion which moved on the outside will create more positive charge on the outside. So now finally we have a very strong electric field developed in this direction. So this is how a potential is developed, what we call as resting membrane potential, right? Here I would like to mention one very important thing, that when potassium tries to move outside, there are two forces going on in opposite direction. One is electric field. See, electric field is in this direction, so it will try to move positive ions this side, right? But under the concentration gradient, since concentration of potassium is high here and it's low here, so under the concentration gradient, potassium will try to move this side, but electric field is trying to push it this side. So this tug of war causes the stoppage of leak of potassium at some point. At that point, so potassium stops to move, and that the potential that we get at that point, that we refer to as resting membrane potential, right? Now all this concept, it is important to understand, to know how resting membrane potential is developed. But once it is understood, you don't have to remember all these concepts. The takeaway from all these concepts are few things. One is that on the cell membrane outside, more positive ions are developed. On the outside, more positive. Inside, they are more negative. We understood already how, right? And therefore electric field is in this direction. Therefore if we have to give a potential, suppose point A and point B, potential electric field and potential, if you have to give suppose B with respect to A, it will be minus 70 millivolts, right? So positive outside, negative inside, electric field, potential this much. Second thing, the pumps that were used, the first was sodium potassium pump, and the second one sodium leaky channels. And the last thing that we have to remember is that on the outside there are more sodium ions and chlorine and calcium, and on the inside we have more potassium. And in fact, that's why we say that cells are bag of potassium, because they have a lot of potassium ions inside the cell. See, I told you that under the concentration gradient, sodium ion will try to move outside, but still, since there is opposing force due to electric field, so they will not be able to go as much, and still at the end the concentration of potassium ion inside the cell will be higher compared to outside. So these things you have to take away in this lecture. Okay, so with this we finish the concept of resting membrane potential, but to get the complete picture, please watch my next video, which is on action potential. So thank you very much.